So I don't remember where I left. Let me recall what we have been doing. So we are working on Fox space. Okay. And we have defined like exponential vectors. Through exponential vectors, we define Weyl operators. And from there, we by differentiating Weyl, I mean, by each, we got a one parameter group of Weyl operators for each t, W of tu or something. Then by differentiating that, by using the generator, we got an observable. It's an unbounded self-adjoint operators, which I have to prove. So hopefully I will prove that. So we got this unitary group W of tu, where T is a one parameter unitary group, and we got Pu equal to minus I T Pu equal to W of T. Okay. So maybe I mixed up last time. If I had the feeling. The thing is, what we get is IPU is actually, maybe I forgot this I minus I or something, which is equal to d by dt W of tu at t equals 0. That is the right thing. Maybe I forgot the I, or I don't remember last time. So this is the right formula. Okay. Then we proved the exponential domain, which is equal to span of E of x, x in h. Okay.
How do you define the
derivative? You just take the derivative. I mean, d by dt, which is equal to, you just define it like this. W of, no, it is defined on vectors. Okay. It is defined on, it's not defined on everywhere. It is defined on some vectors. Okay. So if something is in the domain xi, okay, something is in the domain if the derivative exists. That is how it's an unbounded operator. It is not defined everywhere on gamma. See, okay, maybe I will recall the whole thing. We started with h, and we have this gamma of h, which is that. Then for any x in h, we have E of x. Okay. Then we define W of y acting on E of x. Okay, which is defined as e power norm y square by 2 minus yx times E of x plus y. Okay. This preserves the inner product, so it extends to unitary. So now we got for each t, we fixed Wt, Ty. So these Wy, they satisfy something called Weyl commutation relation, which I will recall again when I prove something. So now this gives a one parameter group, and now W of Ti, which acts on E of x, but it is extended everywhere. Okay. But at least it is differentiable on E of x. But anyway, if you take any xi where this limit exists, what is this limit? You take all those xi such that this limit exists. Xi minus xi, because W of 0 is identity. You have to take W of identity divided by t, limit t going to 0. That's all. So if this limit exists, then we say xi is in the domain of P of u. Okay. And I P of u equal to this limit. I P of u equal to that limit, whatever that limit. Okay. Whatever that limit. That is what is called I P of u. Okay. This is how we define. Then we proved the limit exists on exponential domain. Okay. We proved this minus IPU. I mean, we proved that E, which is equal to span of course, it is enough to prove for E of x. We take any exponential vector, there this limit exists. Okay, E of x, x in h. Okay. So then we proved that E is contained in domain of P of u. Okay. And we even verified that I P of u, let me put the I P of u also, acting on any E of x is equal to. So, I mean, what we will get, let us just to remember what we will get. If you act W of tu acting on E of x, this is going to be e power minus tu. So t square norm u square by 2 minus tu x, right? And E of x plus tu. Okay. There is a product of three functions, which depends on t. So you use the product rule. Okay. The first function is e power, it's a product of e power minus t square u square by 2. First function, if you differentiate it, it's just e power something. It's just a function. So you will get norm u square by 2 times 2t outside. So as t going to 0, that will go to 0. So you don't worry about the first term. Okay. The second term, if you differentiate, you get this. So if you then minus ipu acting on e of x equal to, you get the t will go away. So it is just ux e of x, right? And you have to at t equal to 0, it is just e of x. That is how you get the derivative product rule, no? You take the derivative and the function at that value, and then take the derivative of the next one. Function at the value of the first one and take the derivative. U prime v, u v prime. Okay. So then you do the next one, then that is going to be, so if you take the derivative of that, that is just, then it is just d by dt e of x plus tu at t equal to 0. And this derivative we found, d by dt e of x plus tu at t equal to 0, of course, is equal to, we found that this is equal to n equal to 0 to infinity, n equal to 0 to infinity, and r equal to 0 to n, right? Then u of n minus r, not u, x of n minus r, x of x tensor n minus r. This sum is just symmetrization. It is basically you symmetrize x power n, x tensor n, tensor u basically. When you symmetrize it, you get this. Symmetrize means you have to act the permutation on the whole thing and then do that. Okay. So if you symmetrize it, yeah. And I think it is n factorial or n plus 1 factorial. I am not sure, because there is something, this is n plus 1 factorial or n factorial. You have to do the calculation. Question mark. I put a question mark. I think it is n plus 1 factorial, right? Because you will take t plus x plus tu tensor n and you are expanding that. See, what you are doing is you will have x plus tu. We did last time, okay? Tensor n minus x tensor n. That is how you differentiate. Then you divide it by t and limit t going to 0. So when you do this, the x tensor n will go away, and the terms t will occur. Higher powers of t will go to 0 when you take the limit anyway. Except 2 square. If you take t square, t cube, if you differentiate, you get t square kind of thing. So they will all go to 0. Only the first linear term will matter. Okay. So that you will have a tu. When you differentiate it, you get u. And for that, you need to have there will be an n plus 1 factorial down, no? So it's basically what I have written is correct. Yeah, it is correct, n plus 1 factorial. Okay. I'm convinced. You also get convinced by thinking about it. Okay. So you get n plus 1 factorial down. Okay. Okay. So x tensor n minus r, tensor u, tensor x tensor r. Okay. So it is this. This is the derivative. So pu is basically this. Pu, I have written the definition. We have computed the pu, and we have computed, and where the last term, which is a derivative, looks like this. Okay. Looks like this. Okay. Okay. Now I give you the assignment, which is a bit more messy, but you better do it. And it's I want you to do the following. E, the exponential domain, is contained in P of U domain. Domain of P of U1, P of U2, up to P of UN. For U1 up to UN in H, of course. So I mean, let me just tell you what you have to do. So this is the assignment. Okay? It's just the product. So if you have two unbounded operators, then some vector is in the unbounded operator. If you apply the first unbounded operator, then the resultant, whatever the resulting vector should be in the domain of the other one. That's the condition, right? If you want to compose two unbounded operators, TS, first you apply S, which is an unbounded operator. You are applying it on the domain, okay, on some domain. So it will be domain of S intersection T inverse of the domain of S inverse of domain of T, right? So I mean, it is just that TS you want to apply. You apply S, and S of Xi should be in the domain of T. That is the condition. Okay, that is what you have to show. Okay, it is enough to show for U1, U2. I mean, by induction it will follow. Okay, it is clear. I mean, it will be clear that it will follow. So only you have to prove it for 2, n equal to 2. Okay, and so what will happen is the following. You have two operators there, right? P of u, I P of u minus I P of u gives two operators acting on some E of x. Acting on an E of x is going to be, first operator is ux, E of x. Okay, but then this is some scalar times E of x. Okay, so this will be certainly in the domain of P of, I mean, P of u2, of course. So you don't have to worry about this. You only have to worry about the next other vector. The other one is d by dt E of x plus t u1. Okay, at t equals 0. You have to show that this is in the domain of P of u2 for some other u2. That's what you have to show. And you have to little bit struggle with this. Not struggle, this is clear. You have to apply that t plus something. I mean, you will have a x plus. So if you have x plus, yes. I mean, it is just taking partial derivative, right? It is, what I'm saying is, if you want to take P of u1 minus I P of u2, you can forget this u1, u2 for you call it a different operator, something. This is just dou by dou s, dou by dou s, dou by dou t, dou by dou s dou t, okay, of this, right? Dou square by w of sx, su1, w of su1, w of, it is partial derivative. It's not second derivative. Okay, w of su1, w of su2 acting on some E of x, right? And at s equal to 0, t equal to 0. Okay. So you have to treat one. So it's clear. You can compute that. Okay. So that is what you compute and show that it is in that domain. So I have done it for n equal to 1. So you can do it. You can differentiate that further. What you will get is something like this. This x power n my x tensor n minus r is there. There you will get u1 plus t u2 or something. Okay. Then this is like a product only. Even though that's a tensor product. You can apply product rule for this. You first differentiate that, differentiate this, differentiate this. You have to, but you have to, I mean, this is like an analytic function, but you have to justify taking the limit inside. Okay, that is, and it is just e power something. It's all dominated theorem will tell you. You know dominated theorem, no? If something is uniformly bounded by something, then you can take the limit inside. Okay, it's because of that. It's a uniform convergence. So anyway, so you do that. So this is one thing. This is one assignment. I'm going to give more assignment. Okay. Okay. So then what shall I do? Find it. Okay. Okay. Now I want to define some new operator. So define A of u equal to minus P of iu. Okay. I return to u is in H. Okay. This is done. Okay. Plus I times P of u. Then A dagger u equal to, I mean, with the same domain. Okay, you can add so all these things. See, the domain of AU is a sum of two unbounded operators. So that will be the intersection of the domain of those two things. Okay. And certainly exponential, we don't know the domain. We still don't know the domain of P of U or P of IU. But we know that exponential vectors are in the domain which are dense. Exponential domain is there. So these operators are defined on a dense space anyway. Okay. Similarly, ADU, this is equal to minus PIU minus I times P of U. Okay. Then it is clear. A of U xi eta equal to A xi A dagger U eta. Why this is clear? This is because P of U is a self-adjoint operator. Okay. Which I haven't proved yet, but which you can actually find it out from it's a self-adjoint operator. Okay. Well, it is at least symmetric is clear. If you go through the definition, it will be clear. What is symmetric is A is contained in A star is what is called symmetry. Okay. A is equal to A star. For that, you have to work with the domain also. Okay. We will go through it, but it's a self-adjoint operator. But it's at least symmetric operator is what is used here. Then you can bring, so this is equal to minus P of IU plus IPU, okay, psi eta. That is equal to, you can take it to the other side. P of IU is a self-adjoint operator for IU also. So you can take it out the other side as xi minus PIU minus the I is outside now. So you have to take the conjugate minus IPU eta. So this is exactly equal to xi, whatever we have defined, A dagger eta. Okay. So then proposition A of U acting on E of X is nothing but UX E of X. It just multiplies. No, it's not a scalar. It depends on each X, and you have to take the linear combination of E of X. Okay. On E of X, it acts like that. You're not a scalar or something. Okay. E of X, it's like an eigenvector. A of U acting on E of X is this. And A dagger U acting on E of X equal to d by dt E of X plus t at t equal to 0. That is how we have defined. So shall I leave this as an exercise? It's just direct application. You know what is P of U? I have written already P of U. P of U is the sum of two operators. One takes the inner product out of E of X. Let's write it. P of U, I P of U. Proof. I P of U acting on E of X equal to, we have found that this is equal to minus UX E of X plus d by dt E of X plus tu at t equals 0. Okay, this is what we found. So what is P of IU? You will get an IU here, which will come out it is conjugate linear in the first variable. So I will come out minus I there, so it will become plus UX, right? There is a by 2, sorry, there is a by 2. By 2. The definition of A and A dagger, there is a by 2. Okay. Yeah, this is by 2. So if you put IU here, I will come out as minus I, and this will become plus. Okay, plus UX. And here you have IU here. No, just IU. So then you take the plus with the other one. minus I of minus I P of U. Now, here it is plus I P of U, right? So A of this or A dagger of this? I think A. So I P of U, I P of U, P of IU equal to I, if I take it out, minus I will come out. So it is just UX I times. Now we have I times this. So we want to compute what is I times Q. You have to multiply by I again, right? Minus I P of IU is this. I mean, I'm sorry. I will leave this also as assignment. It's just computation. You will get used to this, okay? I'm sure these things are true, okay? So this is also assignment. Assignment 2. Okay? This is assignment 2. And assignment 3 is more important. And this is the actual assignment. Okay? I mean, this is just I'm giving you because I don't want to go through the calculation now, which I didn't. I mean, which is a bit messy. But I will tell you the idea. Okay? Assignment 3 is, so you have got AU and A dagger U. Okay, AU, A dagger U, just verify this. Then you verify that. Verify the following. Let this is equal to finite particle vectors. You know what is finite particle vectors? Which is just I mean, which is just this is the nth particle vector, is the nth direct sum. Okay, Fock space is defined like this, right? Gamma SH is equal to C direct sum H direct sum H. The symmetric terms are 2 direct sum H, symmetric terms are 3, like that. Okay, so this is the infinite direct sum. You take only the nth direct sum is called n particle vector space. Okay, you just take finitely many linear combination. That is what finite particle vector space. Okay, it's just the linear combination of n particle for all n. Okay, but you have to take the closure. That is what gamma SH is. Okay, so you are only taking so that finite particle vectors F. This is just a dense subspace. Finite particle vectors are dense subspace. Okay, that's not everything. If you take the closure, it is everything. Okay? The closure is you have to take it in the direction topology, which is L2 topology. It's like a small L2 kind of thing. I mean, you have to take vectors in everything which should converge in norm in L2. I mean, the different L2, not okay. So this is contained in domain of PU. It's enough if you prove it's in domain of AU and A dagger U, which both determines the domain of PU anyway. So this is contained in domain of AU, and script F is contained in domain of A dagger U. Okay, for all U in H. Further, AU acting on some V tensor N. Okay, is equal to this inner product UV times, I think, n power half or n, yeah, I think n power half times P tensor n minus 1. It'll this AU is what is called annihilation operator. It annihilates one particle. Okay? It's in the nth particle vector that will come down to n minus 1 particle vector. In particular, it will kill the vacuum vector. I'll write it again. 1 second, let me just check the right formula. I shouldn't be making mistakes. Yeah, AU of, yeah, I have written it correctly. Okay, whatever I have written is correctly. N power half, okay, times UV times V tensor n minus 1. N minus 1 tensor. That's all. This is clear. It's V tensor n, which is an n particle space. It brings down to n minus 1 particle space. In particular, AU acting on the vacuum vector is 0. Okay. And it acting on one particle vectors. For example, AU acting on the one particle vectors. The Hilbert space H is there in the first summand, no? H itself is there. Acting on V, okay, is just UV. UV times phi. Okay. So this is what, so this is, that is why this is called annihilation. Annihilation operator. What is the spelling of annihilation? ANN. Annihilation. I believe it's correct. Okay. These days we don't even check spelling. I write it, it gives the right spelling. No, so I think this is the spelling of annihilation operator. Okay. And A dagger U acting on any V tensor N equal to summation summation N R is equal to 0 to N minus 1, right? So R is equal to 0 to N minus 1. V10, it is just a symmetrization. So what it does is the following. You take the N particle vector. It takes an inner product with one of the vector and brings it down and keep the other one. For the other thing, it just takes V tensor N. It takes it to the next vector by attaching this vector. But if you just attach, it's not in symmetric Fock space, no? I mean, in the general Fock space, you can attach one vector on the left or right, whichever way you want. But here you have to symmetrize it. So that is what we are doing. V tensor R, tensor Q, tensor N minus R. N minus R, right? So R equal to 0 to N minus 1. Okay. So this is what annihilation. For example, A dagger acting on the this vacuum vector is just U.
One. Isn't it from R equal to 0 to N?
Huh?
Isn't it from R equal to 0 to N?
No, it will R equal to 0 to N. You get N part. You have to get the V tensor also, no? Why is it R to 0 to N? 0 to N minus 1. There are only N of them, no? There are only N places where you can put this U. Totally, there are N plus 1 places. One place has to, so, I mean, some. It will start with U. No, what is it? It's a, well, let me write it. V of tensor N minus R. Okay. No, it is basically totally V power N is there. V tensor N is, you are just taking V tensor N and putting this R. So totally there should be R terms for V. So N minus R plus R is N. So R equal to 0, this will be V power N on the starting. R equal to N, it will be 0 on the, it should be R equal to N, right? Yes, sorry, R equal to N. It's not R N minus 1. R equal to N. Sorry. You are right. Good. It's R equal to N. So this is a long exercise. I can give more marks for this computation if you do that. Okay. The point is you have to, I mean, what do you have to do? V tensor N, you know how it's defined. It is just the nth derivative of E of V. Okay. It's the nth derivative of that. You have to differentiate N times. Okay. That is how you get V tensor N. Now you are going to apply A dagger U on that. Okay. Now use the definition. Okay. You will get it. I mean, it is just, you know how A dagger U, A of U acts on exponential vectors. If you differentiate the exponential vectors N times, you get this. You differentiate it and you justify it for the limit and other things. Okay. If you give the arguments, then it will follow. It is just some, if you sit through one night, you can find it out. Okay.
So we need to prove those two statements.
Correct. Yeah, finite. No, you have to say that limit exists. That is what it means by finite rank, finite particle vectors are in domain of AI. First, you have to prove the limit exists on.
So F is in the domains.
Yeah. And then it is precisely this. I mean, you can, along while proving limit exists, you can prove this also. This is what the limit you have to prove. It's the same thing. But you have to justify the limit exists. I mean, that's all. So if you do the calculation, you get creation and annihilation operator. And I have shown that this satisfies the adjoint relationship. I put a dagger, not a star, because for star, you need to precisely know the domain and other things. Okay. This only satisfies on the exponential domain, it satisfies an adjoint relation. Okay. That is what we have verified is it satisfies this adjoint relationship. Yeah, it's here. So whatever I have written. It satisfies that adjoint relation. This just means A of U is contained in A dagger U star. Okay? That's what it means. It does not mean A of U is, I mean, A dagger U is not the star of A of U. Okay? It is just the A dagger U is contained in A of U star. Okay? So that is why I put the A dagger. Not so we are only defining it on the exponential vector. I mean, we are only using this kind of. I mean, we haven't really worked on the domain, okay? Whole domain. Okay? But in the antisymmetric Fock space, there is antisymmetric Fock space which I defined. There, these things are very nice operators, bounded operators, and everything. Okay, so you can actually it's a better place. But then there you don't have Weyl operators. I mean, directly like this. Okay, so after this, let me prove the final one. But what is that I want to do? See, there is some Von-Neumann double comitant theorem. I will prove. I'm tired, so I will prove it in the. I mean, it's the same, almost the same thing, except you have to take care of strong topology. I proved it for finite dimension. Von-Neumann double comitant theorem. Along the same line, we can prove it for infinite dimensional also. I mean, what we can prove is the following. If we have a strong topology, if we have some A, so this is Von-Neumann double comitant theorem. I'm just stating the theorem. Here. Okay. Which says that if A is a star algebra, okay, I mean, you can take just a set and the star closed another thing, but let us just take the. Okay, let me make it different. If S is some set contained in B of H, such that S is equal to S star, okay, that is X is in S, implies X star is also in S. Okay? Then S double comitant, you take the comitant and then the comitant is a star algebra, and this is equal to the algebra generated by S, okay, and then you take the closure in the strong topology, not norm topology, strong topology. We define the strong topology. It is just the closure in the strong topology. So any algebra which is closed in the strong topology is what is called a Von Neumann algebra. And for it to be a Von Neumann algebra, it has to, so definition, any M contained in B of H is a Von Neumann algebra if M is a star algebra and closed in strong topology. Okay. But then this statement is equivalent to saying M is equal to M double comitant. Okay. Take M, take its comitant, all operators with commutes with the all of M, then take the comitant again. That should be equal to this. If we have a closed, this has an analog in Hilbert space. If we have a closed subspace, okay, then you take the perp. Double perp is equal to the original, or the closed subspace generated by S, generated by any set is going to be M double perp. If you have a set S contained in a Hilbert space, then F's double perp is the closed subspace generated by the span closure of S is S double perp. It's very similar to that. Why am I saying very similar to this? We will using Weyl operators, I will tell you. Okay, I will tell you. This is an interesting thing. I mean, maybe we'll prove or you check it. The point, this is the point. Proposition. H, we have a sub H. Now we have a H1 contained in H. Okay. Then you can define as M1 is equal to all those W of X, where X is in H1. Okay. Then, I mean, and then take the double comitant. I take the double comitant. When I take the double comitant or strong closure, that means take this star algebra generated by this is star. I mean, W of x star is W of minus x.
H1 is any subspace.
H1 is subspace, closed subspace. Okay. Then you take the double commutator. That gives you a phenomenon algebra. If you have a, this is star closed. W of x star is W of minus x. Right. Okay. So this is star closed. Okay. So if you take the double commutator, you get a phenomenon algebra. Okay. But then M1 commutator is nothing but W of y. Y is in H1 per.
M1 is a phenomenon algebra.
M1 is a phenomenon algebra. You take the double commutator. You take the phenomenon algebra generated by H1 using W of x. That gives you a phenomenon algebra. You take the orthogonal complement. That gives you a phenomenon algebra. This is precisely the commutator of these things. I mean, if you take the double commutator, so in the per, if you, in terms of, see, this H is in some way, this W of x is a representation of the Hilbert space H. Okay. And that representation preserves the commutativity of the orthogonal subspace. If orthogonal subspaces corresponds to commutator, they are in different commutative. I mean, they are independent. This is some sort of independence, okay, in probability language. So this is just for intuition. You can directly prove this. You can work with this. Okay. Let us come to that. Before that, I want to prove the following. So this is the proposition I want. Maybe you can prove this later. The proposition I want to prove is, so provided phenomenon double commutator is proved, which I will do it next class or in some of the class. So this is just H is a Hilbert space. Hilbert space. Then the W of x. W of x is in H. Okay. This double commutator is equal to B of gamma S of H, all operators. This is equivalent to saying W of x is in H, commutator is equal to C times 1, the identity. Right? It's the same thing. In B of H, I mean, you know this, no? You can prove that, but we haven't proved it anywhere. But see, this is something very easy to prove. If we take matrix algebra, MN, okay, how will you prove that if something commutes with all matrices, then it is scalar? How will you prove that? You take all, so you take some matrix, okay, call it Aij, and Aij commutes with all matrix. In particular, it will commute with Eij, the one in the ijth place, everywhere else 0. You use that relationship. You will get that it is a scalar. Ei should be equal to Ejj and Eij equal to 0 when I is not equal to j. You can just use the matrix algebra. So you can do the same thing with this is infinite dimension. You can do that. Every operator and Hilbert space is infinite matrix. Of course, not every infinite matrix will not give an operator, but every operator will get an infinite matrix. Okay, using the same idea, you will get that any operator which commutes with all operators is scalar. Okay. So because of this, if you prove that W of x in x double commutator equal to C1, then it is same as saying that W of x. Yeah. But how will I prove that? Scalar. C is just all lambda inside. Scalar times identity. So I have to prove the second statement. Okay. If some operator commutes with all of W of x, that is scalar. Then that means the commutator, double commutator of this is B of gamma. I mean, every operator commutes with C, so we get the first statement. Okay. Okay. So, okay, let T W of x equal to W of xt. Okay, let T is in some operator in B of H. It's a bounded operator, W of x, for all x in H. Then,
do we like take a representation of them and then do it, or
Representation of what?
like the way we did it is we assume they were matrices, right?
Yeah.
But here they are just.
Yeah, matrices are up. What is the difference? I mean, you take an algebra and
And
no, it's a. I mean, what you are representing as a matrix.
Yeah, that's what I'm asking here. Like,
There is nothing. There is no difference between a matrix and it is just your convenient way of writing, fixing an orthonormal basis and writing it. So what is it?
No, you can have like algebras which are not matrix algebras. Right?
Sure. Matrix algebra
So
means
this is true for even those.
B of H.
The double commutant.
Double commutant theorem is generally true.
Yeah. So like.
No, there also we proved for finite dimensions.
Yeah, and that was we proved only for like matrices active on some.
No, finite dimension algebra, finite dimension operator algebra. No, matrix means what? We proved for any A contained in M and C, which is same as B of Cn, right? It's the same thing. So we proved for that. What else? Where else it can be proved? You see, when you take the commutant, you have to fix the universal algebra, right? Universal algebra is M and C. There is nothing else. Which is, I mean, I hope there is no difference. You don't differentiate between M and C and B of C. Both are same, right?
Yeah.
There is no difference. Okay. Are you asking that it's for a general algebra, need not be matrix algebra? But then what is a universal algebra? Where are you going to take the commutant?
That's what
There is nothing like that. It's specifically for B of H. Yeah, this is for B of H. I don't know. If you ask algebraic geometer, they may have something more general theorem. See, all this, there are this Gelfand-Neymar theorem, all these things have a analog in algebraic geometry, which is more general. I mean, so there, I don't think so. I mean, but people might have come up with this for general rings and general algebra, non-simple algebra.
Like if we have a like orthonormal basis to mapping to another orthonormal basis, then it will be like a matrix only. That's what.
Say it again. What is it?
So like if we are mapping from a Hilbert space to another Hilbert space, where we have to orthonormal basis.
Infinite dimension also. Yeah, that is what I'm saying. The same proof in finite dimension. No, for what? For fundamental double commutant, it's a different thing. The commutant of B of H is scalar. For that, you just take the same thing. It's like you can treat it as an infinite matrix and then you can work it out. So that is different. Yeah, this this double commutant theorem is for B of H, and you have to take the commutant in B of H. It is not true. For example, if you take some algebra, closed algebra, C-star algebra, or even a Feynman algebra, you can take a Feynman algebra, general Feynman algebra contained in B of H, something. Now you can take an M naught contained in this. Then if you consider the commutant, M naught commutant intersection M, this will not satisfy the double commutant theorem. Double commutant theorem is specific for B of H. Okay. These are what are called type 1 factors. Okay, I mean, there is a language, it's called, see, there is, if your Feynman algebra is a trivial center, a scalar, I mean, everything commutes with, that's what a factor is. Factor is like, if you have something, T, B of H is a factor, T commutes with everything in the B of H, then it is a scalar. If some M satisfies that property, that is what is called factor. Then anything which satisfies the center, M intersection M prime, which is equal to the center of M, equal to C. See, every Feynman algebra will have identity because M equal to M double commutant. Okay, so so identity has to be there, right? It contains commutant of the identity will commute with everything. So identity is there. Okay, so identity is there. So if only identity scalar is there, then the scalar is the only thing which commutes with everything. Then that is what is called factor. This factors is a very interesting theory, but I mean, if you do MSc here, if you are interested, we can discuss these things courses. Okay, so these factors are divided into 3 types called type 1, type 2, type 3. Okay, type 1, all of those things which look like B of H. In the sense, it will look like B of H tensor 1 contained in some B of H tensor K. In B of H tensor K, you can write it as B of H tensor 1. No? This is how all type 1 factors will look like. Okay? That's called type 1. It is like what are called discrete probability space. Okay? And there is a continuous probability space, non-atomic, this is an atomic probability space. atomic discrete probability space. Okay, there is this. These are all probabilistic analog. On the other hand, non-atomic probability space corresponds to what are called type 2 factors. Okay, type 2 factors. If it is finite, it's called 2-1 factor. If it is not finite, it's called 2 infinity. Type 3 is there is something which is absolutely that is not used in general probability theory, which is some sort of non-sigma finite. We deal with sigma finite measure space. All theorems are stated for that. Non-sigma finite measure space are almost useful and almost useless in probability theory or something. Okay, everything is sigma finite measure. But this is very important. Type 3 factors are there, which is like non-sigma finite. So they are very important, not just in mathematics, in physics also. It's a very interesting theory is there. Okay. So these are all, why am I talking all these things? So there are these. So that is why only for those B of H, this double commutant theorem is true. You have to take, where you are taking the commutant is very important. Okay. So when you talk about whatever algebra, you have to say where you are taking the commutant. Okay. So the general theorem for this, whether it exists for, without referring to any operator or any representation, I mean, operators are represented in B of H somewhere. It's not just an algebra. It has a representation on some Hilbert space. So without that abstract theory, whether it is there, I don't know. Okay. So, no, what am I doing? So, yeah. Let me recall what I have been doing. What we are doing, H is a Hilbert space. Then W of X, you take the Weyl operators and T commutes with all Weyl operators, then it should be a scalar. That is a statement. Right? The commutant of Weyl operators is scalar. So the double commutant is B of X itself, B of the Fock space itself. Okay. So this is what I have to prove. T W of X equal to W of XT, then T in B of H. Right. Okay. Now so T W of X equal to W of Tx, right? Then T of P of U E of X equal to W of X T E of X. P of U, P of U. Right? Because you are going to take W of TU. I mean, P of U is a vector, it has to act on some E of X. It's not true everywhere. We want to talk about this relation. This is true everywhere on P of U, right? So what is this? T of P of U acting on E of X equal to T acting on limit T going to 0. T is a bounded operator. W of TU minus 1 E of X divided by T. Okay. So you just keep the limit. T is a bounded operator. You can take the T inside. Okay. It commutes with W. It commutes with the identity, of course. So T will go all the way up P of X. Okay. So then you have the limit. You are assuming the limit exists. So you take the limit out. So I mean, in particular, what I'm saying is T E of X is in the domain of P of U. Okay. And we see there is a proof of this theorem. This the commutant of W of X is everything. There is a proof in KRP, but he is using all this Gaussian distribution and all that. Again, it's very probabilistic, which of course I don't want to do. So I'm trying something. Okay. Hopefully it works. If it doesn't work, I will tell you. I mean, we'll think about something else. Okay. I haven't verified it by hand. Okay. So this is clear. Okay. Now, when T of E of X is in the domain of if T commutes with W of X for all X. Okay. In particular, T commutes with W of Tx. Okay. Now you can take this T all the way up to E of X, cross the limit. It's continuous. Okay. So because that is equal to this, so the limit exists. Okay. So this implies T of P of U equal to this. Equal to this. Okay. This is equal to limit T going to 0 W of tu minus 1 divided by 2 T E of x. Okay. So since that is equal to that, this implies that limit exists. So T of E of x is in the domain of P of u. Okay. Which need not be a which need not be a exponential vector, is in the domain of P of u, and P of T of E of x is equal to T of P of E of x. Okay. This is okay. Now it's clear that both A and A dagger are linear combination of P's, right? So this implies P of A of E of A of U E of x equal to A of U P, no P, sorry. T of A of U E of x equal to A of U. What I have written? No, I have written some nonsense here. What I have written? You are objecting. T of P of U. I said it orally, but I wrote something else. P of U of E of x equal to nothing but P of U P of U acting on T E of x is equal to this. Okay. I mean, whatever I have written that statement, that implies T of E of x is in the domain of P of U, and P of U T E x equal to T. I mean, P of U and T commutes basically when you apply it on E of x. That's what it means. Okay. So, but then creation and annihilation operators is a linear combination of P of U. Okay. So that implies T of A of U E of x equal to A of U T E of x. This means that it's a T of E of x is in the domain of creation and annihilation operators, and this is true. Okay. And T of A dagger U E of x equal to A dagger U T of E of x. Okay. Okay, now I mean, see, this is all from E of x, you want to go to finite particle vectors. They are all some sort of limits of these things. Okay. So, and T is continuous operator. Okay. So believe me, or use this exercise, T of any xi, finite particle vectors, T of A dagger U, A or A dagger, okay. A of U xi, let me write the statement and give you the explanation, is equal to A of U T xi for all xi in finite particle vectors. For all finite particle vectors. I mean, should I write? Because you will be doing that exercise for creation and annihilation operator, no? So to do this exercise also, I am not asking you to write the assignment, but this will be clear. Okay. The same thing will do because you are going to write that as limit. Okay. And T is the earlier what you have used, T is a bounded operator, so you can take the limit out. With the same prescription, this will work. Okay. Okay. So, so there is something I forgot. So you have proved, so I was planning to ask that in the exam, but anyway, now I have to use it, so I have to tell you now. Okay. No, the point is, see, there is something which you see. We have said that A of U acting on V tensor N, okay, is equal to V U V, okay, times that n power half times V tensor n minus 1, right? But this is on V tensor n. That is not everything in the finite particle vector space. From this, by doing something, by taking linear combination, by doing something, You get this kind of things. Finite particle vectors is these kind of things. V1, this symmetrization of this. Basically V1, I mean, it is just V1, this is V, this is the symmetrization, right? V1, V2, V3, up to Vn, right? In this, it will act differently. Okay. Okay. So how it will act is A of u will act as follows, which will be summation. Okay. So I may still ask in the exam. So this is just A of u will act as summation. You have to take the inner product with u vi. Okay. Summation over I equal to 1 to n. Okay. Then then the remaining symmetrization. Possibly that n factorial n will be observed somewhere. I don't know. Okay. Then this is a summation uvi. Now it is just v1 up to vi minus 1 vi plus 1. The I will be missing there. Okay. Because that you have taken it out with inner product. Okay. Vn. Then unfortunately I have written v and confused the whole thing. Because I used u, I've used the v. I mean, this should be a small v, all these things. I mean, I'm sorry. This is small v. Vi. Okay.